Jim Rich accepted to give this talk on this subject, on this exact subject, neutrinos in cosmology. Please.
Okay. Yeah, so this was, in fact, a talk I gave in November 2015, which is not very long ago compared to the Hubble time. So it should still be good, but I just looked briefly at these slides half an hour ago, and so I think they more or less correspond to what you might want in this talk. So I'm not even sure who I gave it to because it's not even said there, but I mean, I think it was the French Physical Society. So how do I do this? Okay, so a little bit of, for a lot of you may not know much about cosmology, but here's something, let's see, how does this work? Here's a sort of a graph of the density of the universe log scale versus time. And what you see is that at the beginning, so this is log time, so there's a radiation epoch where the density is going down very fast. Then there's a matter epoch when the radiation gets redshifted. And then there's today, which is the temperature is about 2 millielectron volts, 0.2 millielectron volts. And then now we're in what's called the vacuum domination because they discovered that the expansion is accelerating. So this is sort of what's going on. Is this, now can I shift this? Yes, okay. So there are various interesting things that go on in these things. There's nucleosynthesis. That's where they form the helium and so forth. And then there's recombination. That's where they form atoms. These are both recombination things here you form nuclei, here you form atoms. So I'm discovering this as I go along. Let's see what's next. Oh, yes. So the role of the neutrinos in cosmology is summary. In the early universe, it's the number of neutrino species. I mean, in the early universe, things are very, very hot, so you can sort of more or less forget about the neutrino mass. And so it's just the number of species, because each of these species gives a black body. So it increases the energy density, and to make things come out right, it changes the expansion rate. So it makes things, adding neutrinos increases the expansion rate, makes things go faster. So you have less time to do things. And then it will also give there are two things that have done that come from this, is that it has an effect on both of those recombination events where you form bound states. There's the effect on nucleosynthesis and there's an effect on recombination. And both of those come because when you add a neutrino, things go faster. And so you have less time to do things, okay? And so the result will change. In the late universe, it's no longer the number of neutrinos. Oh, of course, that happens. What is most important is now the neutrino mass, because now the neutrino mass will complicate the late time expansion, because suddenly one of the radiation components becomes a massive component. And the fact that we don't see any of these complications, because we can sort of now measure the expansion rate and so forth, that gives limits like this, 0.2 to 0.1 electron volt, okay? Actually, I think that should be 1, yeah. Okay, whatever. The limits are not to be taken, the precise values are not to be taken too seriously. So for instance, if there is one, let's see, I'm trying to learn what did I say here? So there's one particular, for instance, there was some talk the other day about hot dark matter. We thought the neutrino of 15 electron volts could be all the dark matter. That's very easy to kill, we'll see, because that really screws things up as far as the late time formation of structure. And then there are also intriguing unorthodox dark matter candidates like a 5 keV sterile neutrino. This would be called warm dark matter. And these things are all going to change what happens at late times, and the fact that we don't see these things is going to put constraints on them. And see what else? I have another line here, yes. And then, of course, there's the super challenge now to detect those. And if I have a little bit of time, I'll mention that at the end. So what I'm going to go through, I think, on the next slide, I'm going to start back here on the early universe, the number of neutrinos, and talk about how we know that the number of neutrinos is equal to 3 from cosmology. Knowing, of course, is also a question of believing, because these are all model-dependent limits, and so we might want to talk about how you'd have to change the model. So, early universe, the number of neutrinos is equal to 3. The neutrinos is 3 more black bodies besides the photons. Okay, They're the same as except photons, except they decouple much earlier at a temperature of about a megaelectron volt instead of an electron volt. That's because they only have weak interactions. Fermions instead of bosons, so that means they have a slightly different thermal distribution. It's not so important. Left-handed neutrinos and right-handed antineutrinos reach thermal equilibrium. The wrong helicity states, people always ask us, what about the wrong helicity states? They're not expected to be present because they never reach the thermal equilibrium. Their interaction rates are too small. So we're not counting all the neutrinos, we're just counting the ones that couple. Because the others don't have any reason to have a thermal distribution. They might be there because God put them there, but they're not there because of interactions. So this is actually, I do a lot of teaching in cosmology. This is a gold mine of examination questions. You can show that the neutrino's temperature is a little bit less than the photon temperature. There are all these funny ratios of integers that you get in statistical mechanics, which makes teaching fun. Okay, 4 over 11, 3 over 11 to the 1/3. These are great things. Okay, but that's not what we're going to talk about here. So what can a neutrino do in the early universe? They have only weak interactions, gravitational actions, but both interactions play essential roles. Okay. For the weak interactions, they give you the initial conditions for nucleosynthesis. For instance, this is a graph of the neutron-proton ratio versus temperature. So this is the temperature, 10 megaelectron volts, 1 megaelectron volt, 100 keV. So time is going this way, and this is the ratio of the number of neutrons to protons. And what you can see is that it's going down, and this is all determined by the neutrinos. How did they do that? Well, in the beginning here, there's a thermal equilibrium between neutrons and protons because the electron neutrinos are hitting the neutrons and turning them into protons. And this happens very fast. So you get a thermal equilibrium between N and P. So the ratio of neutrons to protons looks like what Mr. Boltzmann told us it would be. It would go down with temperature e to the minus delta M over KT. So it goes down like that, okay? Then at this point here, do I have a stop? Well, yeah, here the interactions stop because the density is not sufficient to make this interaction effective, but they still have free decay, so the neutrons now decay, well, like that. And then at about 60 keV, that's when the reaction rates are such that you can now form deuterium, and so you have nucleosynthesis. And since now the neutrons are trapped in nuclei, they're fixed here. So what you see here is this whole thing here. The initial conditions are set by this interaction. So if you didn't have neutrinos, you wouldn't know what the initial neutron-proton ratio would be. But this reaction here tells you it has to be something in thermal equilibrium, which is this. So this whole curve here is just determined by the number of neutrinos. Now, the other thing is, and of course, this doesn't allow us to measure the number of neutrinos because, first of all, it only is determined by the electron neutrinos. Where the number of neutrino comes in is in the expansion rate. The expansion rate is given by Mr. Friedmann's equation here. It's just the A is the scale parameter, so the Hubble constant squared here is just proportional to the matter density, the photon density, the neutrino density. So at the time of nucleosynthesis in the radiation epoch, these are the things that dominate, and the more neutrinos you have here, the more black bodies you have, the bigger the expansion rate is going to be. That means that the temperature drops faster, and that means that you'll have less time to have all these nuclear reactions going forward. So it reduces the amount of time. So this is it. Expansion rate in the early universe is dependent on the number of photons plus the number of neutrinos. Number of photons is 1. We know that's true. If you have more than 3 neutrinos, the temperature drops faster. That leaves less time for neutron decay, which gives more helium than the observed 25%. This is the take-home line here. The more neutrinos you have, less time for neutron decay. That gives more neutrons, which results in more helium. This I don't think should be here. That should be later. So just look at that. Let's talk about this, because this was now something that was known 30 years ago, 40 years ago. This is an important article, Cosmological Limits to the Number of Massive Neutrinos. It's in 1977. Gary Steigman, very prominent authors, Steigman, Schramm, Jim Gunn. And they say here in 2000, here they say this was at an epoch where statistics weren't very serious. They said, it is shown that the observed limits to the primordial abundance of helium-4 lead to the constraint that the total number of heavy leptons, that means neutrons, must be less than 5. Okay, they don't give a confidence level or anything like that, so serious as that. But I mean, you can see now that it's 5, and at that time, this was before, this limits came out before LEP and so forth. The number from particle physics, I think the limit was 100 or something like that. And now in the modern, in 2015, the same analysis now gives the number of neutrino species between 1.8 and 4.5, and we now give confidence levels. That's 95% confidence level. And this was in 2005. It's changed a little bit since then. And of course, the physics there is that if you had more neutrinos, the expansion would be more, and so you'd have more neutrons because fewer neutrons would decay. So that's a very simple physics, and it gives a simple number. It says that the 3 is more or less what you expect. The other thing is this comes out, a confirmation comes from the CMB. And this is a famous plot of the Planck image of our last scattering surface. That's the Z equals 1,000 surface. And these are hot areas, cold areas. The image is blurred because the photons random walk in the 100,000 years before recombination. If you increase the expansion rate, this reduces the time for random walking, and it makes the image sharper. Okay, that's the physics there. And so this is just a little picture how the photons random walk, and they're viewed by the, I did this with LaTeX. It's not easy to put a picture on LaTeX there. Diffusion distance proportional, the geometric mean of the photon mean free path, and CT walk, which is one of the expansion rate. So there you go. So the Planck damping. So the blurring is seen in this famous plot here by the fact that there's very little power. This is the temperature fluctuation power as a function of angular scale. So these are small scales. These are big scales. So this is the famous peak. And you see out here, it's at small scales, there's very little power. That's because the image is blurred. Okay. Okay, and why is that? Because the photons are random walking over a time given by the expansion rate. And if there were more than 3 neutrinos, that would give less time to, let me get this right, that would give less time to random walk and therefore less blurring. So the blurring they see is consistent with what they expect, and they get at 3 sigma less than 4. So this sort of makes things hard for sterile neutrinos, the ones that were inspired by the reactor anomaly. It says that any sterile neutrino must not have thermalized. That means that they wouldn't be present to contribute to the expansion rate. And this is, I think, a pretty solid thing. If it turns out there's a 4th neutrino, well, that will mean something was wrong in the cosmological model. But people don't have any good ideas how to get around that. How am I doing for time? Danielle. Time? Fine, okay. How much time do I have left? 10 minutes left. Oh, okay. So, take a break? Yeah. So this is, I think, what's most interesting for this meeting is that any sterile neutrino must not have thermalized. In other words, it must not be present with an abundance given by T to the 3rd power. It must be less than that. So the problem with the reactor neutrino anomaly was that the oscillation parameters that they required certainly indicated that it would have thermalized. So this is ruled out. The sterile neutrino inspired by the reactor anomaly is ruled out by, say, 3 standard deviations. This has changed a little since 2015, but not much. It's a little bit stronger, actually. Voila. Now becomes the thing that makes people a little more interesting now is massive neutrinos become non-relativistic when KT is equal to mass of neutrino c squared. Neutrino oscillation experiments tell us that there's at least 1 neutrino with m nu greater than 0.05 electron volts. So what happens is that now it changes the way the neutrinos contribute to the energy density, so it modifies the expansion rate through the equation. Okay, that's that. And that modifies, since the expansion rate is what, through the Hubble law, tells you relation between distance and redshift, that's going to modify that, and that's what, we don't see any modifications that would be implied by a neutrino as massive as 0.2, as massive as 0.2 electron volts. So the fact that we don't see any modifications of that indicates that it's probably less than 0.2 of an electron volt. Let me see if I've got something on that next. Oh, okay. So limits on the neutrino mass. When T equals the mass of the neutrino, the energy per neutrino becomes constant. It's just equal to m nu. It modifies the expansion rate, modifies the distance redshift relationship, which implies a limit. Very simple physics saying that it has to be less than 0.23 electron volts. That's using Planck data plus BAO data. I guess I won't have time to explain what BAO. That's what I actually work on. So if you have questions, I can talk about BAO. Now, the other thing they do is that they start to contribute to structure formation, because now all of a sudden something that didn't clump, a massless neutrino, or relativistic neutrino, can now, as soon as it becomes non-relativistic, it can start participating in the formation of structure. And here it becomes a little more complicated to calculate. And there are limits that are now starting to cluster around 0.12 electron volts. That's from the structure seen in the Lyman alpha forest of quasars. I'm not sure everybody knows what the Lyman alpha forest is, but it's a spectrum. It's the distribution, spatial distribution of absorbing clouds between us and a quasar. And this is by my colleagues at Saclay, Nathalie de la Brouille. In 2015, there are a few more other groups and other techniques which give limits like this around there. This tends to favor the normal hierarchy, and it is hoped in the next generation of experiments to get that down to about 0.05. So actually maybe get a significant measurement of the neutrino mass. So this is looking at, this is more complicated. It's looking at the spectrum of inhomogeneities and see how they're modified by neutrino mass. So now the question is, it was mentioned, it's always mentioned that these things are model dependent. If it turns out that there is a neutrino mass greater than 0.2 electron volt, how must we modify the cosmological model to recover agreement? Because it depends on the cosmological model. For instance, time-varying dark energy, that doesn't work very well. The best thing to do would be just to say, well, inflation gave us a funny initial spectrum of perturbations, which cancels the effect of the massive neutrino to make it look like the neutrino has no mass. So that's the sort of, I think, a take-home you can get on this. The simple cosmological models give that. If there is a mass that's that means you have to put something weird into the cosmology. Put in a spectrum that tricks you into believing that the neutrino has got a low mass. So there you go. So, I wanted to say something about hot dark matter. This is a 15 electron volts hot dark matter. This has been eliminated for a long time. Here, when mass of the neutrino is 15 electron volts, it gives the right matter density for today, but it causes problems for the cosmic micron vector spectrum because it modifies the expansion rate before recombination. So the CMB spectrum is strongly modified. And also, it destroys all structure below the scale of galactic scale. So there basically be no galaxies if this were the dark matter. So that's mostly of historical interest, but at the time people were doing NEMO and so forth. Not NEMO, what was the thing at CERN?
Nomad.
Nomad, yeah. This was a popular thing. This was one of Maury's mistakes And in retrospect, it probably was a mistake. That's just how free streaming works. It just means that neutrinos free stream destroys short wavelength perturbations. So 15 electron volts, galaxy-sized perturbations are destroyed. At 4 keV, small galaxy-sized perturbations are destroyed. So the fact that we see small galaxies, the fact that we see structure in the Lyman alpha forest, tends to put limits on 4 keV. You can't have anything, dark matter made of anything lighter than 4 keV. So that's my last thing here, 4 keV. I'm a little bit disorganized because I'm surprised how these are coming out. Warm dark matter density is too high if they're 100 per centimeter cubed. So they must have been formed, have not been formed in thermal equilibrium in the early universe. One possibility is produced by oscillations. This is the famous Goddardson-Woodrow mechanism, which is now pretty much ruled out. So they destroy, so the neutrinos free stream until temperature of 4 keV, so homogeneities on scales of small galaxies are removed. This is good because few galaxies are seen. So this is sort of an opposite. So 4 keV is not, this slide seems to say that 4 keV is not really excluded, and it's only excluded to weakly excluded, but say 6 or 7 keV is certainly excluded. So fine-tuning, once again, the neutrino mass is just big enough to allow for the existence of galaxies. This is the way one of the reasons I don't like this stuff is that all of a sudden, you know, galaxies, which were supposed to be astrophysical objects formed by cooling and so forth, their size is determined by some particle physics parameter in the fundamental Lagrangian. That's very strange. 5 minutes, okay. That's actually, we're going to get there. Okay, this is the last thing I had to say. The ultimate challenge would be the detection of cosmological neutrinos, charge current interactions. They have charge current interactions only on radioactive targets. That's why they're hard. Okay, for instance, we know that tritium decays with an endpoint of 17 keV. We saw that yesterday. So that means that if you can take this antineutrino and put it on the other side, you can have neutrino plus tritium giving helium-3 plus electron, with this recoil electron having an energy which depends on the neutrino mass. So the capture electrons separated from the beta minus electrons by 2 neutrino masses. I think Steven Weinberg was the first to notice that. So if you had a 100-gram tritium target, you could have 10 captures per year, and 3 times 10 to the 24th tritium decays. And that's, of course, the problem. You have to be able to have a very modest, by SNO standards or Kamioka standards, target 100 grams, but you have a large number of decays for 10 captures per year. So this is actually the Ptolemy experiment. If you're interested, read this. They actually, some people mostly centered around Princeton. I think that means Princeton something or other. They have a project to do that. And if you're interested, please read it. It's the ultimate in ambitious experiments, but it's a technique that's similar to the stuff that's done for tritium beta decay. Conclusion, neutrinos have an essential role in cosmology and nucleosynthesis by determining how much helium is produced. May have something to do with dark matter, though that's unlikely. Cosmological observations consistent with 3-light neutrinos, direct detection is somewhat difficult. Thank you.
Thank you, Jim, for this talk, which was exactly in the spirit of what we were expecting. Do we have questions?
This number nu comes out, nu smaller than something. Do I understand well that it is active neutrinos up to a certain mass, or sterile neutrinos up to some other mass, and anything in between with a mass which is a function of the mixture of the two?
Well, it's the number. It's just a measurement of the number of black bodies that are present. That's strictly speaking what it is.
Right.
So there are 3, and for normal neutrinos, and even for for sterile neutrinos, it's not so much the mass that counts. So the mass has to be less than electron volts or something. It's the mixing angle. Because if if the sterile neutrinos are produced by the Donaldson-Woodrow mechanism, it's the mixing angle which determines how much is coupled. So at very small mixing angles, you don't ever produce them enough that they get into thermal equilibrium.
Right. So I have to divide the number by the excess number by the mixing angle?
Yeah. But the thing is that the mixing angle for the reactor neutrino anomaly was sufficiently high to guarantee that thermal equilibrium would be reached.
I see. So it would be good to have a graph that allows us to understand what we're talking about.
I'm sorry.
He has it. Okay.
I forgot that.
Right.
Someplace.
Over there.
Thank you. Valerio Pironello from Catania University. I would like to know, there is any estimate of the mean free path of neutrinos before decoupling?
Well, it's just standard. It's just standard charge current and neutral current interactions. I mean, these are done in Boltzmann codes. It's a dilute gas. They're moving.
Yeah, but I mean.
What is the?
Yeah.
What is? Oh, you want a numerical example?
Well, as a fraction of the.
Well, let's put it this way: when the neutrinos decouple, the age of the universe is a microsecond, I think, and so the mean free path is going to be the inverse of that. Now, what's the speed of light? Is 1 foot per second. So it's 10 to the minus 6 feet. Was that?
I think.
What?
Couples at 1 second.
No, that's.
Couple at 1 second.
Oh yeah. Okay. Yeah. What am I? The microsecond is what? It's something. Yeah. It's one. Yeah. No. It's 1 second. Yeah. You're right. It's 1 second. So it's a second. So it's 10 to the 9th feet. No. 10 to the 10. No. In a second they go. It's 10 to the 9th feet. Yeah.
Pierre.
Yeah.
Yes, Pierre Ramon, Florida. You mentioned
Please.
Okay.
Please.
What? Okay. You mentioned that you thought the mass limit on neutrino could be brought down to about 50 milli-electron volt, if I understand correctly. What is the time scale for that?
Well, there are
And which
projects in the next 5 years. Next 5 years, we should have that.
Really?
But you see, this is. We'll see. At any rate, like I say, the important thing is to remember is these are fits of the spectra of fluctuations seen by various tracers.
Sure.
And so you have to take them. You interpret them correctly. It's not as limits on the mass, but limits on the mass unless something funny is happening.
Other questions? Yes, Cecilia.
I remember vividly that at one time the number of neutrinos was 2, and absolutely not 3 from cosmology. And also I would like to know, if possible, just to say a little bit about what we learned from Planck. I mean, except getting out of those B modes. Did we learn something really new and interesting?
That's an interesting question. Well, I think for one thing, the 2 neutrinos, I mean, since the 4 neutrinos had no confidence level, I mean, you always have to put confidence levels on this. And at the time you're probably talking about, people weren't doing error analysis very clearly. So I don't know the result you're talking about, but I suspect it's just because people weren't doing error analysis as rigorously as they do now. For what Planck, I think the fact that they now measure 3 neutrino species with a precision of about 0.3 is a great triumph. I mean, you have to. I mean, if it had been done before WMAP, there would have been 1,000 things that they did much better than before. But the fact that WMAP came first, they did a lot of, for instance, WMAP plus BAO proved that the universe is flat, and this sort of. Those are the interesting things we've learned from cosmology. The universe is flat, and it's consistent with 3 neutrinos and so forth. There's nothing particularly funny. Plus, of course, the funny thing is lambda, but the CMB doesn't really contribute very much to that. That's low redshift stuff.
Find lambda funny?
Well, yeah, if you have
It makes me
depends
sad.
on your sense of humor. Does it make, what do you think about it? Does it make you feel?
I don't like it.
Because you think that, yeah, I mean, well, we can talk about that.
I'll tell
John.
you, I don't like black holes either. I hate them.
Okay.
John.
John Loseco, Notre Dame. Jim, what about supernova? We know that neutrinos play a very critical role in supernova, and is there any dependence on these properties that we're interested in? I know people talk about, for
it's an
example,
interesting
measuring the hierarchy by looking at the suppression of the neutronization pulse, but are there other things you can
I mean, well, the neutrinos are important there because they give the number of, they have, once again, the number of objects which reach thermal equilibrium, so it, but, you know, I'm not an expert in that. I mean, I don't know if the models are sufficiently accurate to do as well in cosmology. Cosmology has the advantage at that point of being very linear, and supernova is not very linear.
Other questions? Yes, over there.
May I add a comment that, of course, cannot be present in the slides because 1 month ago there was a new letter of intent for the Ptolemy experiment. It was published on the archive, so if someone is interested.
Okay. This is the neutrino detection experiment. Are you involved in that? Oh. Are you talking?
Any other question or comment to Jim? No? If not, thanks again.